We can begin. So, good morning, everyone. Um, so, yes, Seba, it's blank. No, is it good? Okay. So we will go into more details. So we cover briefly what ground motion models are, the main components, but today we'll go through their formulation and understand why they are structured the way they are. And as a motivation, you remember, I think in the second lecture we saw the complicated equation of how modern ground motion model looks like. So now we will try to understand why this complexity is needed and what each term is trying to achieve. But before we go there, we will go through a review of the previous material and actually let me change the order of the slides and maybe we can actually start with reviewing the assignment. So who here had time to read this? Are there any questions that maybe you had by reading the assignment, or should we go question by question and kind of discuss what the expectations are? Uh, so there are three problems. And the first problem is sort of covering like the general understanding and make sure that sort of the fundamental ideas are clear in our head. Then there is a problem related on magnitude recurrence, similar to what we solved in the on class on Wednesday, and then performing a simple hazard calculation. So for the first one, the first question, what is asking you is to think about the idea of seismic moment accumulation and release. And we talked about balancing a fault, so the energy or the seismic moment that is accumulating is the same amount that needs to be released. So if we were to think about how we are releasing this energy, what would mean for if this energy is released with magnitudes ranging from 3 to 4 versus a larger magnitude event? So how many 3 to 4 magnitudes are needed to release the same energy as one magnitude 7? Um, is this clear as an idea? So you can do the calculation, you know the equation to calculate the seismic moment for each magnitude size and compare the seismic moments that you get. And as a hint, you will see that the energy that you release with a magnitude 3 or a magnitude 4 is negligible compared to a magnitude 7. So the assumption that like having multiple small events sort of eating away energy that can be spent on a large one is not a valid one. The second one is maybe even more broad, but again, think of like what is the mechanism that generates earthquakes. So earthquakes are generated because tectonic plates like move relative to each other, and that happens due to the convection currents in the mantle. So stopping earthquakes, would it mean in terms of plate tectonics? And why do these convection currents exist in the first place? If you remember, it's like the temperature and density differential that is causing them. So like, I don't know, think of like maybe like wild ways that someone could revert that and what that imply and how complex or infeasible that solution is versus what we are trying to do in practice as earthquake engineers. So the problem too is on magnitude recurrence. Uh, we saw last time the different magnitude recurrence models, the truncated exponential, the characteristic, and the maximum magnitude, and we kind of discussed like the regions or sort of the scale at which each of these models apply. So the first question essentially asking you to write all of this down, and then specifically like for a well-characterized fault such as the San Andreas fault, which of these uh, recurrence relationships will be most applicable. And the second question, like when we, like the problem that we solved in the class, we have the dimensions of the fault and the CR modulus. And then based on that, we can compute which is sort of the preferred magnitude that would be consistent with the dimensions of that fault. And then doing the balancing of the seismic moment for different magnitude recurrence relationships, and what does this imply in terms of the number of earthquakes for like, as you saw, I think maybe in the second lecture where we saw that increasing the maximum magnitude reduced the activity rate, because if you are allowing more larger earthquakes to happen, then that means you cannot have that many small ones. And then you can plot all of them to compare them with each other. This is I don't think that it would be easy to do this by hand, but like should be very straightforward to do it in Excel. But if anyone wants to program it, is completely fine with me. And you can use very simple integration schemes if you are to integrate the density function of these different relationships. So you can use the trapezoid rule or even the rectangle rule, where it's the amplitude of the density function times the integration width that you are using. And then the last question is on the seismic hazard. So first, compare what is the difference between deterministic and probabilistic seismic hazard analysis, and where as the modelers or as the analysts, our assumptions, where do they fit into each of these frameworks? So in deterministic hazard analysis, we need to choose the percentile and what are the sort of decisions that lead us to choosing an appropriate percentile, and what is the equivalent thing that we need to do in the probabilistic seismic hazard. Then for the hazard equation that we saw and we are going to see over and over again, explain which of these terms are doing them and group them as you see fit. And why here we are integrating over the magnitude and the distance. And then the third part of this problem is for these three scenarios where we have the rate, so how often they happen, and the median, and the standard deviation in log units to give us the density function of the ground motion. Compute the hazard for these three cases. So you can, here we don't need the integral because we know the specific magnitude and distances. These are discrete, so it's simply the summation of the rate of this event times this term, which is the probability of the ground motion exceeding some value for that scenario as defined by its magnitude and distance. And maybe if this is not, we can go through maybe one case here, just make sure that everyone is clear on how to do it. So if you were to use, for example, Excel, first we need to define the different ground motion thresholds. And because it's a log normal distribution, using thresholds that are like spaced equally on log normal scale makes the most sense. So we can start from, I don't know, 0.0. Can you see, or is it small? Can increase it. And then also in log scale, 0 is not defined. So we need to start from a positive number. So we can start from 0, 0, 5, 0, 0, 0, 1, and then let's say 0.03, 0.05, 0.07, and then follow that scale. So this times 10. And maybe to 3G is more than enough. Now, let's say for scenario, for the first one, we have the rate, which let's see how much it is. It's 1 over 300. So this is 1 over 300. Here. I will show it both ways. So we can even, so remember that the ground motion variability is defined in log space with a is defined as a log normal distribution. So that means that we can either take the logs of the ground motions and apply a normal distribution, or we can apply a log normal distribution. But it's either all the calculations need to be carried in log space or all of them in linear space with the appropriate distribution. If you mix and match, then you may encounter issues. And typically, it's more straightforward dealing with normal distribution. So when I end up doing these calculations myself, I convert all the ground motions into log units and then do these calculations with assuming that everything is normal distributed. So for that reason, we will take the log of the different values. And when we take log here, we mean natural logs. And now for the hash, we can compute P of SA greater than Z. And then we can compute the hazard. So for this one is the function norm dos dist. And then we have the test value, in our case is ln of z. We also, let me make some space to keep track of them in insert. So we have rate, median, and standard deviation. So the median is here natural log of 0.44. And the standard deviation is 0.65. 0.65. So this one should be norm dist, and then the value that we want to evaluate the distribution, the mean of this distribution, and the standard deviation. And then cumulative or the probability mass function. Which one do we need? Or maybe neither of them. Exactly. So true for cumulative. And then 1 minus that, because we need the probability of exceedance. Okay. And to compute the hazard, what do we need? The rate with? Correct. So the rate that is given in this case times the probability of exceedance. So now if you take this column in this column, and we also plot them on log-log scale, this is the hazard curve for the first scenario. So this is the ground motion, and this is the annual rate of exceedance for this particular scenario. And you will repeat this for all three scenarios and then sum them, and that will give you the total hazard. Yes, please.
Row number 3, in which you have written median. I think that should be mean, right? Because you have taken the log of median, that is mean in the log scale.
This should be the mean, you say?
Yeah, is that median or should that be mean?
In a normal distribution, the mean and the median is the same number, is the same. So like the normal distribution is defined in terms of its mean and its standard deviation. So in that sense, it should be the mean, the thing that goes into the equation. But also because it's a symmetric distribution, median and mean is the same. Median may be the only reason that it may be safer to call it median is because percentiles are independent of transformations. So the median of the log normal distribution is the same as the log, I'm sorry, the median of the normal distribution is the same as the log of the median of the log normal distribution, because that's defined based on the 50th percentile, whereas the mean of the log normal distribution is not the same as the mean of the normal distribution. Like you cannot take the log and yeah. Any other questions for the first homework? It should be straightforward, but if there are any other questions, let me know. I think this one is the only thing that I don't think we have directly covered in class. We should cover it in the next few lectures, but also before even seeing the answer, think about how do you get the fraction. Like if you have the hazard curves for all the scenarios and the total, how would you get the contribution of each scenario into the total hazard? Okay. And as I said, it's fine to work together, but in the end, each one should submit their own answers, and I will assume that you will stand like on your own, you stand behind your answer. So like if this is for you to practice, not just to give an answer. So like whatever it's written down should be like clear in your head. And if something is not, then we should discuss it before moving further. So let's also do a quick review of the previous lecture. And maybe we saw some of them already in the homework, but very briefly, can someone tell me what are the two approaches that we saw for seismic hazard analysis? Yes, please.
DSH and DSH.
Correct. And then also, what are the key assumptions, or like where does the user input goes into each of these frameworks?
In the deterministic, we have a governing scenario, and there is not a frequency related thing like
Correct?
in probabilistic. We take the relative contribution of all the pods and distance.
Yes, absolutely. So in the deterministic, as like sort of the analyst, how do you go from the scenario to the ground motion? What decisions do you need to make?
We have like we know the main governing like faults or area sources. We calculate the ground motion intensity at the site, and then we see which is the largest one.
Yes,
The largest one is the governing one.
but if I can again push you a little bit back, if you have the magnitude, you have the distance from the governing scenarios, is this on its own sufficient to give you the ground motion, or do you need to you need a third parameter that you need to decide?
Yeah, the ground motion model, from that we can get the uh, standard deviation and the mean. So
Yes,
for a particular percentile, we can calculate.
exactly. And you need to choose what percentile you will select. Yeah, great. And then what is the equivalent thing that is done in the probabilistic seismic hazard analysis? So there, maybe we didn't cover it. So can anyone maybe take a guess? Do we have one ground motion model or do we have many ground motion models?
Many.
Yes. And how you weight those ground motion models is a decision that you as an analyst needs to make based on how applicable you think each of them is for the site of interest. So that's where sort of again we as analysts weigh into how and affect how the answer that we get. And again, maybe a quick question: how like when we are dealing with, like, let's say an important structure versus a regular structure, how does the importance of the structure fit into the calculation of its approach? Yes, Abba. Yes, and the more important the structure is, percentile of exceedance. Yes, and in the probabilistic, yes, and in that case, the more important the structure, the smaller the annual rate of exceedance that is allowed. And if we briefly go to even the hazard curve that we created, so it's the y value that you select to reach the corresponding x value. So as you design a more and more important structure, you want it to withstand more and more rare ground motions that are defined by the rate of exceedance. And the further down you go into this axis, the larger the ground motion that you get, and it's the sort of your design value. Great. And as an example, for example, this is the guidelines that are used in the deterministic hazard analysis, and this is to show that really the correct approach is to think everything in terms of probabilistic terms and account for the frequency of the earthquake. So even in the deterministic analysis, this is for dam design in California. The way that you select the appropriate percentile, so whether it's the 84, whether it's the median, and so on, has to do both with the severity of your like the importance of your structure and the consequence that a collapse of that may imply, and also how frequent the earthquake it is. So if you're dealing with frequent earthquakes, then that means that you may have more than one earthquakes during the lifespan of your structure. And so relying on the median ground motion may not be the safest choice. Whereas if you have earthquakes that may happen, I don't know, once every 500 years, and you know your structure will be there for only the next 50, then even if you have an earthquake, most likely its ground motion will be around its mean, and so choosing the 50th percentile is a reasonable choice. One last thing to clarify from the previous lecture that I think I had one question is what the unit of dyne is. And that's a unit of force in the imperial system, and it's defined as the force that a particle that is 1 gram, that has a mass of 1 gram and an acceleration of 1 centimeter per second square will exert. So this is equal to 10 to the power of minus 5 newtons. And I think there was, or I think I asked them this question, this equation in the previous lecture also seemed to be a little bit confusing. So are there still any questions, or is it more clear why the problem is structured this way? And kind of, if this is, so in the simplest case where we think of discrete scenarios, the way that to compute the hazard is the rate of each of them times the probability that they will create that ground motion. And to consider a range of scenarios that like a continuous distribution, we have the integrals, and maybe the way to see the equivalence between the two is to think of like how we would have numerically integrated the relationship at the bottom, where like the simplest way that you integrate is you have the function that you want to integrate, and then you compute the value at each point, and then the area under the curve is that value times the width of from the integration. And if you go if you were to apply that rule in the equation that we saw before, then for each discrete scenario defined by its magnitude and its distance, the rate will be equal to the density function for that magnitude times the density function for that distance times the width of the integration for the magnitude and distance values. So now going to the ground motion models, I think we also saw it before. There are 3 main groups of ground motion models. And so depending on each region that you are, you should perform your analysis with a ground motion model that was developed for that region, because these different regions have very different scalings in terms of distance and magnitude. And the 3 main groups were the sort of shallow and shallow faults that you can find in the Western US, in Japan, in Taiwan, Turkey, Greece, and New Zealand. Then we have the cases around the world where we still have faults, but the crust is a lot deeper, and those earthquakes happen a lot deeper, and those are the stable continental regions, and those are the types of seismicity that we have in our neck of the woods, in Australia, in Africa, and so on. And then we have the very big earthquakes in subduction zones, like the ones that we have in Oregon and Alaska, and around Japan, Chile, Taiwan, and so on. And for these for these regimes of earthquakes, we have varying sizes of available datasets, with the largest typically being for the shallow crustal regions, because we have higher seismicity, and those regions are better instrumented. And so depending on the region, the models that are developed could be a combination between being based on empirical data and numerical results. And this is the case, for example, for the most recent group of ground motion models that are developed for the West Coast and other active regions. And you see all of the data are coming around California, Nevada, and Taiwan, New Zealand, and so on. And again, kind of to recap, and as we move forward, is in the ground motion model, we define the input is the scenario, so which is defined by the magnitude, the distance. the site conditions, and the output is the distribution of the ground motion. And this is what we covered. So because not in all regions we have the same amount of available data, in areas where we have a lot of available data, they will primarily develop empirically, and in areas where we don't have available data, so we don't really have that many earthquakes, for example, that go to magnitude 8s and 9s in subductions, and for those we will use simulations. And then one of the challenges that we face in this area is when we do research is how do we combine simulations and empirical results to develop a coherent ground motion model. And the other thing that we need to recognize as we will go through the equation is that this is not like pure statistics as an effort, because the data alone, like in any region, we don't have enough data, especially for the rare earthquakes that we want to design to purely perform a statistical fit. So there needs to be some underlying physical behavior to control how the ground motion should scale to the scenarios that are not well represented in the data set, and those are the ones that we typically want to predict. So if we were to go to have them, damn it. But maybe I have a figure later just to make the. So this is, for example, the magnitude distance distribution from the previous iteration of the faults. So all of the data that we have are, the majority are 3 until 5 and 6, and they are for distances between 20 and 100 kilometers. But really the scenarios that dominate our hazards are the ones that are here, which is where we don't have data. So those are the big earthquakes and the earthquakes that happen close to that site, because those will be the ones that dominate. And so to go from the data here to predict the earthquakes that are here that are missing, we need to have some constraints from some physical constraints to do that correctly. And so the way that a ground motion model will try to achieve that is by assuming a certain functional form. And I think we saw something similar before. So we have the magnitude scaling, and this magnitude has a linear magnitude scaling and a quadratic scaling that we will see why is needed. Then we have the distance attenuation, and we separate it into geometrical spreading and an elastic attenuation. So the geometrical spreading has to do with why the seismic waves attenuate as the volume that they occupy expands, or the wavefront expands. And then the anelastic attenuation has to do with the attenuation due to impurities in the crust and the dissipation of energy as the seismic waves travel. Then we have some parameters that account for the different styles of faulting. So how the ground motion from a reverse normal fault chain is on average different compared to a strike slip fault, or how the depth of the earthquakes affect the amplitude of the ground motion, and then the site amplification that is captured by the VS30 and other parameters such as Z1, which is the depth to 1,000 kilometers per second. So how did we decided that this is the appropriate relationship to try to fit? The simplest model that we have in seismology is what you will see in literature either called as a Brun or as an omega squared model. And the way that you come up with this equation is if you assume you have a homogeneous medium, and in the middle of that you have a circular crack. So this is the simplest way to model an earthquake. You assume that the epicenter of the earthquake is at the center with a finite dimension, and then it starts here and it expands to the boundaries of the crack with a constant velocity. So if you were to to derive the equations for this type of a slip input, this is the relationship that you will get. And you have a constant, and then your ground motion scales as a function of the seismic moment. So the larger the seismic moment, the larger the ground motion. Then you have the source spectrum, which is define the amplitude, the frequency content of the ground motion at the source. So what frequencies and how its frequency is the amplitude of its frequency that is generated at the source. Then how it attenuates with distance. And then last, the amplification and the attenuation at the near the site. And the source spectrum is given by this omega squared spectrum that has this decay that is proportional to the square of the frequency. So a slope of 2 in log units, and that's where it gets its name from. And so maybe, so this is the how the source spectrum would look like. This is for different size of earthquakes for the same stress drop. And the corner frequency defines where the break in the amplitude happens. So whether you have like this, the slope or the constant path. And you will see all of the source spectra have a slope of 2 in log scale, and that comes from that power. In general, so different parameters that define our scenario control different parts of the spectrum. So the amplitude, and especially at the higher frequency, at the lower frequencies, this is controlled by the magnitude. How high the source spectrum is, this is controlled by the stress drop. And then the attenuation and the side effects control the higher frequency of the frequency amplitude spectrum. So the moment magnitude defines the amount of energy that we release, and then the stress drop defines how compact this energy is. And so the corner frequency, where does this break in the spectrum occurs? One way to get a feeling of the source frequency, of the corner frequency, is that it's inverse proportional to the time that it takes for the rupture to happen. So the longer that the time the rupture takes to happen, the smaller the corner frequency is. And you can also relate that with the stress drop, because if it takes longer for the rupture to happen, it means that the energy is not as compact in time as a higher stress drop would have implied. And the way that you can get the source duration, so how long it takes for from the time that the crack starts to the time that it reaches the outer boundary of where you assume the crack will extend, is the distance, the radius, divided by the rupture velocity, which you can assume it's around 3 kilometers per second on average empirically. So we can go through a calculation to see how the corner frequency will change here for a magnitude 5 and a magnitude 7. And so to do that, like as a back of an envelope calculation, first let's calculate the area of that rupture. And can someone tell me how would you calculate the area based on the size of the earthquake?
All displacement times the width of the point.
Yes, and once we combined all of those equations into one, do you remember the equation that we got? No? It's okay. But you're correct. So we assumed like a constant aspect ratio, and that allowed us to, like, we defined the seismic moment as seismic moment equals to mu d times the area of the rupture. Using the aspect ratio, we were able to like solve either for width or for length. And then by assuming a constant stress drop, we also had a scaling for how the displacement scales with the area of the rupture. So we saw that d is proportional to the square root of the area. And when we combined all of these equations together, we got that, let's see, mu equal, terrible. I'll do it here. We got that mu equals log of area minus 4. Because it's approximate, we don't, yeah. So then we have that area is 10 to the power of magnitude minus 4. So for a magnitude 5, what would be that? And this is, the area here is defined in terms of squared kilometers. So 10 to 5 minus 4 is 10, so 10 square kilometers. And if we assume an aspect ratio of 1.5, then we'll have then the length will be the square root of 10 times 1.5, and that will be 3.9 kilometers. And then how would we calculate the source duration? Yes.
Yeah.
And what is dr here of the circle? So for this example, it would be so. And this is how sort of we will go from this simplified model to how we can use this relationship to approximate the real case. So here we actually assume that it's a rectangular crack. But let's say that because it's like a back of the envelope calculation, that it's a small enough deviation that this model still works. We can assume that either the rupture initiates somewhere at the center of the rupture plane. So if this is 3.9, then the distance that the rupture can propagate will be 3.9 divided by 2. Or we can assume that the hypocenter is somewhere at the edge of the rupture, in which case the distance for the rupture will be equal to 3.9 kilometers. Right? So here the Source duration will range between 3.9 divided by 3, it's 1.3 seconds, and half of that is 0.65. So the source duration will be between 0.7 to 1.3 seconds. Yes, Abba? It's black. It's visible now? Thank you. And so the reciprocal of that will be 1 over 0.7 will be, and then 1 over 0.65. So it will be between 1.4 to 1.5 hertz. Is this clear to everyone? Yes, please.
DR.
DR is the distance that the rapture will travel from its initiation point to where it terminates. So in this like circular track, you can assume like it's this shaded circle that expands slowly to these outer edges, and so dr is equal to the radius. Here, if you assume that the epicenter of that event is somewhere in the middle, and so the rapture will propagate simultaneously this way and that way, it's more or less half the length. And if we are closer to like unilateral rapture, so the earthquake starts somewhere here and then it propagates over the entire fault, it's closer to the length of the rapture. Any other questions? Yes.
So DC is going from 0.7 to 1.3, so the reciprocal of 1.3 should be less than 1.
Yes. What did I do then? Yes. Sorry, you are absolutely right. Um, 0.7 and then 1.3. So it's from 0.8 to 1.4. So can we quickly now do the same thing, the same calculation for a magnitude 7? What would the area be?
1,000.
1,000 or 10,000? 7, yes, 1,000. 1,000 square kilometers. Can we assume a constant? Okay, what would be the can we assume a constant aspect ratio? Let's assume a constant aspect ratio for now. Instead of calculating the length of the rapture, let's first calculate the width of the rapture to see if that makes sense. So what would that be? Could you please repeat? Yes. Is this a reasonable value? When we saw the magnitude scaling versus displacement, where would that relationship fall apart? Or what is the thing that is limiting the maximum width? The crust thickness. So if this is a strike slip fault, what would have been, and it's like in a shallow active crustal area, what would be a reasonable crust thickness? 60 or 16 or 60? Yes, around that 16, 15. Yes, it's not a constant value. So this 25 is larger than that. So it means that it can't grow that big. So now, if we assume a width of 15 kilometers, what would have been the length of the rupture? Yes. And now TC, or the source duration? From 10 to 22 seconds. So corner frequency will be from 0.05 to 0.1. And so if we go back, that's why we see the corner frequency, so where the slope changes is moving to the left as the magnitude is increased. And you see for a magnitude 7, our quick approximation, so this is the corner frequency is where the amplitude is equal to the square root of 2 of the amplitude of the peak. So it's about here, and you see it is more or less around 0.1. Is this clear? And now, because we are not doing this like for no reason. Like the thing to recognize is that how much the amplitude is changing as a function of magnitude before and after the corner frequency. So if you see here, if you are at a frequency that is below the corner frequency, you have a factor of 30 every time, 32 every time you increase a magnitude unit. So if you go from a magnitude 5 to 6, your amplitude increases by a factor of 32. Whereas if you are above the corner frequency, so the higher frequencies, that's only is increasing by a factor of about 3 every time you increase a magnitude. And if you are in between, where for small magnitudes you are below the corner frequency, and for large magnitudes you are above the corner frequency, you see that a linear scale doesn't apply anymore. And this is exactly why we need this linear and quadratic scaling to capture this behavior that we get from physics, from a simplified model. So here you see that for a small frequency, so if we were at 0.3, we are crossing the corner frequency as we go from the small to the big event, and that's why we have this factor of 30, this factor of 3, and then the like a quadratic shape, and that's why we need the quadratic term here to bridge between the two. Whereas if we are at a very high frequency, that even for a small magnitude, we are above the corner frequency, we just get the linear scaling that continues with the same sort of increase at higher magnitudes as the intermediate or small frequency. And this is what is changing the like. So here we were looking at amplitude spectra, but this is the same reason that we get this behavior in the response spectra. So these are the average response spectra for a magnitude 5, 5.5, 6, until 8. And if you are to normalize all of them, we see that the smaller magnitudes have a sharper decay at the large periods. The period is the reciprocal of the frequency. So this part of the spectrum here is the equivalent part of the spectrum here. So small frequency is a large period because one is the reciprocal of the other. Is this clear to everyone? Or are there? Yes. Why are they converging? Here. Typically, this may be a little. Let's see. So far we discussed only about how the magnitude is scaling the shape. We also have the effect of the kappa. So our actual spectra are not flat, but they have this decay at the higher frequencies. So if you were to take now, if you were to try to compute the response spectrum from this amplitude spectrum, from this Fourier amplitude spectrum, at the very high frequencies, your oscillator will not resonate with the input ground motion at the same high frequencies. Instead, we will resonate with the peak amplitude. And so there is, if you were to assume that this scales by a constant factor every time you increase the magnitude, that will imply that there is more or less a constant ratio between the peak amplitude of the spectrum and your PGA, because this doesn't scale with the PGA itself, it scales with where the maximum amplitude exists. I don't think that this explanation is very clear right now, but we can go through random vibration theory in a few lectures, and that will help show why this happens. Is this a sufficient answer for now, or? Okay, thank you. Any other question? Is this, or maybe the question, is this behavior clear? How the shape of the spectrum changes with magnitude. Okay, so we also saw how stress drop or the corner frequency affects our simplified Brun source model. So in the actual ground motion relationships that we have, we don't explicitly account for that. So which are the terms that that capture its behavior? So there is no, like empirically, there is no much difference in the stress drop between different magnitudes for the same style of faulting, but the stress drop is changing between styles of faulting. So whether you have a reverse fault, a normal fault, and also where the earthquake is located in the crust. So this Z dot is if this is the fault plane, and this is our rupture, Z tor is the depth to the top of the rupture. And because the stiffness of the crust is increasing with depth, earthquakes that happen deeper tend to have higher stress drops. So because stress drop is a parameter that is very difficult to compute, instead we use these three terms to try to use a proxy to capture its behavior. Now, the second component of the model has to do with how the amplitude of the seismic waves attenuates with distance. And this is the term that is describing that. So here we have the Fourier amplitude, which is equal to or is proportional to the exponent, to this exponential scaling and this linear scaling. And here, this is what we will call as the geometrical spreading. And this has to do with how the seismic waves attenuate as the wavefront is increasing. So like from simple energy conservation, if you assume that your earthquake starts here and the seismic waves radiates, so they create this wavefront, and like at t plus I plus 1, they are here. Because the energy is constant, if you are distributing it over a larger wavefront, the amplitude at each location has to be lower. And this behavior is captured by the geometrical spreading. And the power n here is the distance scaling that you get for different types of seismic waves. So if you remember, we said that body waves radiate through the bulk of the crust, and so they attenuate with the square of the distance, whereas surface waves only radiate at the surface, and so they attenuate slower linearly with the distance. And the term above is the term that is describing the inelastic attenuation. So this is the energy dissipation that you have because your crust is not a perfect elastic material. And the parameter that describes how fast this attenuation happens is this parameter Q. So the higher the Q, this comes from electrical engineering, so and in search for quality. So higher Q values mean that the material is closer to an elastic material, so the attenuation is smaller. Whereas lower Q is when the attenuation is faster for the same amount of distance. And one thing to realize is that also that the attenuation is captured by these two effects simultaneously. So that's why you cannot switch one model for Q and keep the same model for geometrical spreading. These two models need to go in pair. And you will see that in research, because, for example, different researchers try to either invert for Q or for geometrical spreading. So typically, you need to make assumptions about one to be able to solve for the other. And if we were to connect maybe for what we saw at the second lecture, this is what explains why in the eastern US we see ground motions we can feel ground motions over longer distances. So here the Q is higher, and so like, for the West Coast, between 10, 15, 200 kilometers, you have like a factor of more than 100 at the higher frequencies, whereas in the East Coast is closer to a factor of 30. So over the same distance, for the same magnitude earthquake, you are going to feel stronger shaking. Yes, please.
My coordinate acceleration spectrum shouldn't that be centimeters squared per second?
It's the Fourier amplitude of an acceleration. That's a good catch. So why it is the way it is? How is the Fourier amplitude defined? Is FAS is the integral a of t, where this is your acceleration time history from t to infinity or t max, let's say from infinity, of e times to power of minus I omega t dt, right? So the units of the angular frequency and time cancel out, so you don't get any units from here. This is centimeters per second squared, but you also have here dt, which is seconds. So the product of these two leads to units of amplitude, Fourier amplitude that are centimeters per second. But this is a good cut. So maybe, I don't know if you have seen this before, but if you took, like, for example, courses in signal processing, like from electrical engineering or like from applied math, typically they assume dt to be, or like your integration, your sampling interval to be unit. So you don't have units there, and you don't have this change in units. But if you were to perform the Fourier decomposition for signals that are ununiformly spaced, then you need to account for the impact of dt, and that is what will also lead to the changes in units there. Any other question? Is it clear in general, or is it confusing? Yes, please.
So why the T2 number kilometers? So it is very different contest from others for two graphs.
Why the difference is bigger between 250 as opposed from 50 to 10? That's the question? Yes.
Is below 1, and for the second graph it goes above 1 centimeters.
Correct. So, like, if I'm understanding the question, and correct me if I'm not. So you say, like, here, for example, between here and here, the distance is more or less the same. It is slightly here, larger here, but not that big. Whereas between this one and this one, the difference is much bigger, right? Can you explain? Can you tell me why you think this is the case? Maybe even here, or I will ask you to answer this question, but maybe let's go through this slide, and then it will be your turn. So give me one moment. So just again, to connect between the equation that we are using to fit the ground motion model and the theoretical equation. So we had that the Fourier amplitude is proportional to this power term times this exponential. So if we were to take the logs of the Fourier amplitude, because we model them in log space, now we have this term that is proportional to the log of the distance, plus this term or minus this term that is proportional to the linear distance. And in the functional form that we are trying to fit, this term is what we are trying to capture with this relationship, and then this term is what we are trying to capture. So this term is what we are trying to capture with this term in our model. So in our model, this is the geometrical spreading, and this is the inelastic attenuation. So when in the ground motion models that we use, the coefficient that scales linearly with distance is the inelastic attenuation coefficient, and what is scaling proportional to the log of the distance is the is the geometrical spreading. So now is back to your question. Would this relationship help you understand why the difference is bigger here than, or you see more difference at between 50 and 200, between 10 and 50? And maybe what will also help you is to see that this is on log scale. So do you have any ideas before I give the answer? So all of these are like, there is more or less a factor of 5 between all of them, right? So if you have constant factors, then the effect of the inelastic attenuation is the same. But, or maybe like, if you were to go, if you have distance and you have 0.1, 1, 10, and 100 kilometers, and you have the contribution between geometrical spreading and inelastic attenuation. So, and you say that, so, and we start with some value here and here. So let me, how to say, let's say that our model is x times log of r times y times r, where x and y would be the value of these coefficients for that particular frequency. So from 0 to 1, we'll have a factor of x. Here, the ground motion decrease, 2x, 3x, right? But for the inelastic attenuation, this will be y, this will be 10y, and this will be 100y. So, and, or maybe if we were to start, and this will be minus 10x, and this will be 0.1y. So at short distances, the attenuation from the attenuation from geometrical spreading is what is dominating, but at large distances is the inelastic attenuation. So because this comparison is over large distances, and there is significant difference in the inelastic attenuation between the Western and the Eastern US, that's why you see most of the effect here. Is this helping? Yeah. The geometrical spreading is simply how the wavefront expands. So you don't really see that big differences between one region and the other. So that's why at the shorter distances, you don't expect to see that big of a difference in the distance scaling. Any other question? These are great questions, and thank you so much. Another one area that our simplified model deviates with, maybe we're close to time. So I will give the motivation, and we'll see how we'll address this in the next lecture. We stop at 11 or 11:30. 10:50. Okay, 2 more minutes. So the model that we are basing our functional form is based on a circular rupture. This assumption really breaks apart when we are dealing with extended ruptures, so very big earthquakes. And empirically, if we are to plot the ground motion as a function of distance, both the PGA and the PGV for as a function of magnitude, you see that after some magnitude, the amplitude more or less plateaus. So you have this slope here, and then the amplitude stops increasing with magnitude. So physically, the reason that this happens is that if you are assuming you have a very extended rupture that goes here over many, many kilometers, and here over many, many kilometers, and this is your site, and you have energy radiating from here, 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 and so on. The seismic waves that arrive from the parts of the rupture that are far apart from your site will have attenuated by the time they will reach your site. And so, although there will be a lot of seismic energy released through the entire fault, it's only the shaking at your site will only be controlled by the parts of the rupture that are closer to your site because the attenuation hasn't been so severe. And this is why we see both PGA and PGV plateauing after some magnitude. And the reason that you see the PGA plateauing sooner than PGV as a function of magnitude is because PGA is primarily controlled by high frequency ground motion, and for a constant Q, you lose Q amount of energy every time you have one oscillation of one period of ground motion. So for the higher frequency, you will have many more cycles of those seismic waves to travel the same amount of distance, so higher attenuation. And so the region of influence for PGA is even smaller compared to PGV, that is controlled by longer period ground motions. I think this is time, so we can continue over how we are modeling this on Wednesday. Are there any questions? Yes, please.
The last slide that you were showing. So does that mean that for a given site, we cannot have like there will always be an upper bound on a peak ground acceleration? Because the wave would have
Upper bound is a very strict word to use. Like there is. I wouldn't use the word upper bound because this you only see the effect of distance here, but as we saw even before, we had the aleatory variability, which is like both the within and between, and this is sort of like yes, there is an upper bound on sort of what parts of the fault are contributing, but you can have much larger ground motion here if your site happens to be next to an asperity as opposed to the asperity being further away. And it's very deep, like we don't have at least rich enough data to really see an upper bound in sort of the ground motion that we expect. But in general, we wouldn't see that fast scaling. Yeah. Okay, thank you everyone.